So we've looked at categorical variables and pie charts and bar graphs, but now we're going to turn to quantitative data. Okay, so it's very important that you understand whether you have a categorical or a quantitative variable. When you have a quantitative variable with numerical values, there's other things we can do with them. We're not going to make a pie chart or a bar graph here. We're going to make another type of graph, and the most common that we see in this class are histograms, stem plots, and box plots. Box plots we won't look at more until the next section because we need the quantitative numbers, the 5-number summary, and that's the next section is all about the numerical ways to represent data. But we can, in this section, I'll show you histograms and stem plots. Okay, so those are two ways. They turn out they're pretty similar to each other in a lot of ways. I mean, they're both ways to represent quantitative data. It's often recommended if you have large sets of data to do a histogram, smaller sets maybe do a stem plot. That's kind of just a preference of which one you want to do, but we'll look at histograms and stem plots. You can read through that in the notes, but I'm going to go ahead here. So we'll look first at histograms. So histograms, depending on whether you've had some statistics, you may have never heard this word before. They kind of look like bar graphs, but bar graphs, your x-axis, let's say you set it up the way we did before, your x-axis is categories. Okay? It's for a quantitative variable. For a histogram, your x-axis, or whichever axis you pick, but usually your x-axis is going to be a quantitative variable. So like a traditional x-axis, 0 to 100 or whatever scale we need. And you divide that into these equal intervals that we call either classes or bins. Sometimes they're called bins, B-I-N, just depending on the terminology. But we can say we divide it into these possible equal width classes. And then just like with our categories, you can't how many fall in, but they're not categories, they're intervals. Like between 70 and 80, there were this many scores, if we're talking about grades, as an example I have in a minute. Okay. So you divide one axis quantitatively into intervals, and then you count how many of your data fall into each of those intervals, and then you plot bars with those heights. So it's kind of like a bar graph. I usually say without gaps. There could be gaps if there's none in a particular interval, but the bars can usually touch on histograms. Okay. So first of all, here's an example that I made with a software called GeoGebra, which is a really awesome free software if I haven't mentioned that one before. It was originally, there's a dynamic geometry software called Geometry Sketchpad that costs money, and some people decided they wanted to make a free version of that for students, so they got NSF funding and made this thing called GeoGebra, geometry and algebra together. It's much more than that now. It's really just kind of an all-purpose math software package that is completely free. Just go to geogebra.org or geogebra.com and you can download it or run it off of the web. And I made this graph with GeoGebra here. I'll show you later in a video how to do that. But this, just to give you an example, here's a set of grades. I don't list the actual grades, I just have the counts, but we have some grades from, it's just a made up set of grades to give you an example, but maybe somebody made a 42 or something, there's a grade in the 40s, and then grades in the 50s, 60s, all the way up to 100 possibly. So I have what's called the frequency table here. So if you want to make a histogram, the first thing you do is basically you look at your minimum and your maximum or your possible values and decide how you're going to divide it up. For grades, I would usually divide it into tens because that's the way we do when we assign grades usually, right? Your 80s or Bs, 90s or As, and so forth. So that's what I've done in my table. And then you look at the grades and you see, oh, I've got 1 in the 40s, 1 in the 50s, 3s in the 60s, and so forth. And you count them up and make what kind of looks like a bar graph here. But again, these aren't categories. On a bar graph, you have categories on the bottom, and they're not numerical. Here, it's actually a numerical scale in order here from 0 to 100. And so the height of the bar tells me how many scores fall within that interval, say from 40 to 50. Because they touch, we have to decide which endpoints we're including. The default in most softwares is to include the left endpoint but not the right. So if you look at the 40 to a 40 would fall into that one from 40 to 50. The 50 would fall into the 50 to 60, into the next one. You would include the left endpoint, not the right. Until you get to the end, most software like GeoGebra includes the final endpoint, because say these were grades, you would want to include the 100 there in the A's, so it closes up the last interval. Okay. But that's basically what a histogram is. Before we make one, we want to talk about the shapes of histograms. Now you could get just chaotic stuff that doesn't have a particular shape that you describe, but there are 3 very common shapes that we want to identify when we see them. One of them is symmetric, which means that if you find the middle of the graph and you were to cut it, you basically have mirror images. This picture that I have is actually what we'd call a normal distribution, and it's not perfectly symmetric, rarely are they, but this one's close enough. We'd say it's roughly symmetric. So if I cut that one in half, I almost have mirror images, not perfect, but almost. This one's also what we call bell-shaped. This is a normal distribution. It doesn't have to be bell-shaped to be symmetric, it just has to be mirror images, but this is the most common symmetric type of picture you're going to see, where it is what we call a normal distribution or a bell shape. But you can also have skewed left or skewed right, where they're stacked up high on one side with a long, we call it a tail, on the other side. And a lot of times students reverse this when they're trying to describe it, but be careful here. In statistics, we say it's skewed toward the tail. Okay? So here's a picture of one that's skewed left. We have a peak over on the right and then a long tail on the left. So we say it's skewed to the left. Skewed right would be kind of like a mirror image of that with a long tail on the right. Okay? So again, not every distribution falls into one of these, but a lot of them are symmetric, skewed left or skewed right, so you want to be able to tell if you see one that is. Okay?